Welcome everybody to our first seminar this academic year, and so our speaker is Davide Vittone. He's from the University of Padua, but he's a member here this semester. Please, Davide.
Thanks, Camillo. Thanks for the invitation. Thanks for coming. And it's a great pleasure to be here. I'm very happy able to stay with so many friends, all the new friends. What I wanted to tell about you today is some topics about a theory that has been developed in recent years and which deals with this topic. So Lipschitzgraphs in Carnot groups, and therefore I guess I need to introduce these two objects. So we'll start with Carnot groups and Lipschitzgraphs. So let me say immediately that, especially here in Princeton, I should probably call them stratified groups. Okay, I will tell you what's the difference in a moment. So a Carnot group. So let me give the abstract, the geometric definition or algebraic definition. A Carnot group is a Lie group which is connected, simply connected and nilpotent. This means in particular that it will be diffeomorphic to some Rn, and it has its associated Lie algebra is of a particular form. It is stratified. It can be decomposed into the direct sum of several layers, G1, Gs, and these subspaces form a stratification. Stratification means that every layer can be recovered by, is linearly generated by commutators between elements in the first layer, G1 and Gj. So in particular, G1 generates the algebra under Lie brackets. The last layer commutes with G1 and so also with the whole algebra, and it's not zero. So this number S is called the step of the group or the step of the algebra. Now, under these assumptions, as I told you, the group can be identified with Rn via the exponential map. Actually, the exponential map identifies G with its Lie algebra, which is some Rn. And the Lie algebra is decomposed in two layers. Each of them will be diffeomorphic to some Rn, okay, for some dimensions. So for us, G will always be Rn with some non-abelian group law. And we will think Rn as decomposed into several layers. So coordinates will have different waves. And in fact, this structure allows to introduce dilations. So for a positive lambda, dilation of a factor lambda acts on coordinates with different waves. So x prime denotes the coordinates in this first part of the composition, and it's scaled by a factor lambda. The second part, x second, in the second layer is scaled by a factor lambda squared, and so on and so forth. The last, so those in the last layer, in the S layer, are scaled by lambda to the power S. And it's pretty easy to recognize that when you introduce these dilations, they are a one-parameter family of group automorphisms. So somehow they commute with the group law. So if you dilate a product, you get the product of the dilated set. So up to now, these are exactly stratified groups, as well studied, for instance, by Stein and this school. They are named Carnot groups whenever you endow them with a certain distance, d. So when we fix a distance d, which is left invariant, so left invariant with respect to dilation, it's invariant under left translations, and which is homogeneous, meaning that when you scale the 2 points by a factor lambda, then the distance gets scaled by a factor lambda, okay? You call this guy left invariant homogeneous distance. There are plenty of them. And so when you endow your stratified group with such a distance, you call it Carnot group. So I guess the terminology was introduced by Gromov. And in fact, so why should we care? So why are these objects interesting? One motivation is that they naturally appear in sub-Riemannian geometry. So what happens is that there is this notion of sub-Riemannian manifold, and these objects are the tangent spaces to sub-Riemannian manifolds, in the sense that if you pick one of these objects, of these spaces, these sub-Riemannian spaces, and you look at it at smaller and smaller scales around a fixed point, so your manifold is going to look as a Carnot group. It's close in the Gromov-Hausdorff sense to a Carnot group. So these are natural objects that appear in the theory. And most of the talk will deal with the Heisenberg group, which, apart from Euclidean spaces from Rn, is the simplest example of Carnot groups. For a fixed positive integer n, the nth Heisenberg group, which I will denote by Hn, is the Carnot group which is associated with this algebra. So the algebra is decomposed into two layers, G1. So the first one is 2n dimensional, and it's generated by these objects, by these vector fields, x1, xn, y1, yn. The last one is the second layer is one dimensional, and the commutation relations are given by all commutation relations are zero, except when you consider the bracket between xj and yj, where you get t, so the element in the second layer. When you put in coordinates, dilation looks like this. So xy are n plus n coordinates, and their dilation is standard. You multiply by a factor lambda, and on the last coordinate, the dilation x by multiplication by a factor lambda squared. Okay, so I don't want to specify the group rule, which is essentially irrelevant in this picture.
Just one question. Why is it particularly? Why the Heisenberg group is particularly important among Carnot groups?
For sure, the first one, H1, is the first example, the basic example in the theorem. I mean, the one with the smallest, the non-commutative example with the smallest dimensions. So, and then, I mean, if you want, these are generalizations. So there are Carnot groups. I need to introduce, as promised, intrinsic Lipschitz-graphs. So again, the general problem is to study objects like some manifolds with some intrinsic regularity, some regularity from the viewpoint of the geometry of these groups. And I believe the project was initiated by Gromov himself. And in particular, here I want to focus on the notion of Lipschitz submanifold with some intrinsic Lipschitz regularity. And here the building blocks are these intrinsic Lipschitz graphs. So imagine your group G is decomposed as product of two complementary homogeneous subgroups, W and V. Complementary means that they meet just at the group identity. They generate the group, and they are homogeneous, so invariant under dilations. Okay, and of course, everybody knows, I mean, the simplest example would be Rn, which can be decomposed as the product of Rk and Rn minus k. Okay, let me also tell that, so I will call this guy, so this structure a splitting of the group. And in Hn, there are just a few possible splittings. Well, there are many, but whenever you have a splitting of Hn, then one of the two groups is a vertical k-plane when k is at least n plus 1, so more than half of the dimension. And for me, vertical means will always mean that it contains the direction t, the vertical one, where the dilation scale with a factor lambda squared. And then there is a complementary subgroup, which in coordinates look as a 2n plus 1 a plane of codimension k, which is horizontal. Okay, horizontal means it's contained in this. I mean, in this R2n, the first 2n coordinates. Okay, in particular, when this happens, the horizontal subgroup in the splitting is always abelian, and actually it's isometrically isomorphic to n plus 1 minus k.
So when you're saying possible, you mean it's like a theorem. If you have WV with that property, one of the two has to contain the
yes,
like this line, and then okay,
yeah, there must
how it splits in the other, it doesn't matter.
Exactly. Exactly. Definition. Whenever we have a map from one of the subgroups W in the splitting or a subset to the other subgroup V, we define the graph of phi as the subset of points in the group, in the whole group, that you can construct by multiplying an element in the domain W times its the value of this function in W. So you are multiplying an element in W times an element in V. And this gives you the graph. If you think a little bit about this classical situation, this, I mean, in Euclidean spaces, this is precisely the graph of a map from Rk to Rn minus k inside Rn. So this will be an object in G in the group. And now, whenever you have these graphs, you can give a notion of Lipschitz continuity from an intrinsic viewpoint for such functions. Okay, and this is given in terms of a comparison with homogeneous cone. Okay, so the definition was stated for the first time like 15 years ago by Franchi, Serapioni, and Serra Cassano. So we say that a map phi from W or a subset to V is intrinsic Lipschitz if you can find an open cone. Cone means something, an object which is invariant under dilation, which contains V, actually V minus the origin in its interior. So it's an open neighborhood, conical neighborhood of V, which has the following property. Whenever you move the cone so that the vertex is sent to P by a left translation, so this guy is the cone which moved so that the vertex is P, and you intersect it with the graph, you get nothing. Okay, and this for every point in the graph. So picture is this is V. This is your cone C, which is something homogeneous. So an homogeneous cone around V somehow. And you say that the graph of some function phi is intrinsic Lipschitz if the following happens: when you move the cone to any point P, then this is not meeting the graph except at the point possible. Okay.
So for some reason you decide to draw
yes
the graph from the like,
because it's 20 years that my graphs go in this direction.
okay, so what you call the vertical plane is actually lying horizontal in your picture.
No, the vertical plane is usually at the domain W. I mean, in the interesting
vertical plane, the domain W. Ah, okay.
The domain is W, and in the interesting cases, it's the vertical guy in the splitting.
Ah, okay.
Okay.
Okay. Ah, okay.
Okay, and in fact, the graph goes into some horizontal direction.
Ah, okay. The graph goes into some horizontal direction.
This is in the, I mean, the opposite situation where the domain is horizontal is somehow trivial, okay. And it always reduces to the Euclidean case. Somehow.
So the commutative, the final commutative, the center of the group is actually in your
yes,
in your independent variables.
In W. The center is the vertical line. The center of the group.
Yeah, the vertical is the vertical line, right?
But V is abelian.
So now I'm confusing. Okay, so V
is abelian. You can produce abelian horizontal subgroup only up to dimension n. So there exist abelian subgroups which are also horizontal.
So what you call the vertical K plane is really the domain. Okay, so sorry, that's why it's confusing. Okay.
Yeah, usually the vertical plane will be the domain, and the horizontal and abelian
Okay, is what you call the tag.
the tag.
Yeah, so it's what I was thinking, but you like to put, okay.
Sorry. And I mean, there are by now many evidences that these are the correct objects in the theory that replace somehow, that encodes a notion of Lipschitz regularity. By the way, they were used a few years ago in a quite important paper by Naor and Yang, where they proved they proved the correct, the precise efficiency of some algorithms in theoretical computer science, which eventually they reduces to the possibility of embedding Heisenberg in some L1, and at that point, these objects played an important role in their proof. It's an Annals paper by a few years ago. Okay, so now we have a candidate notion of Lipschitz continuity or Lipschitz regularity for submanifolds. Okay, and one would wonder whether there is any regularity, any good properties for such graphs. Okay, so let me first say that an intrinsic Lipschitz map generally is not better than Hölder continuous. I mean, from a Euclidean viewpoint, so one nonetheless hopes that there is some intrinsic regularity. For instance, one might wonder whether some Rademacher theorem holds in an intrinsic sense. So the problem would be, is it true that every intrinsic Lipschitz map phi is differentiable from some intrinsic viewpoint, in some intrinsic sense, almost everywhere on A, mu W almost everywhere on A. So mu W, I mean, W is a subgroup, so you can put some R measure on it. It's a locally compact subgroup, so you can put, so mu W denotes some R measure on the group. Actually, it's also a nice submanifold, so you can put any reasonable measure you can imagine. Okay, so what should intrinsical differentiability be? So I would say that a map phi is intrinsically differentiable at some point W bar if, when you pick the corresponding point, which is this one on the graph, and you perform a blow-up procedure, then this submanifold is converging to a homogeneous subgroup of G. So, of course, the blow-up is meant with respect to the dilations of the group, the intrinsic dilation. So what we are doing is picking our point on the graph, moving it to the origin, dilating the graph, the object, and we hope that under this blow-up, everything is converging locally uniformly to some homogeneous group, to the graph of a map which is parametrizing some homogeneous subgroup, which is what you can imagine replaces planes in this theory. Now, as I said, the low dimensional case, so when the dimension, when W is horizontal, when the domain W of the graph is horizontal and so abelian, everything more or less reduces to the classical case. So they have classical Lipschitz, so intrinsic Lipschitz graph have also classical Lipschitz regularity, so you can simply use Rademacher theorem. So the interesting case is when W, the domain, is vertical and the target V is horizontal. And so the domain W has high dimension and the low dimension. There was a case which was known since a few years, codimension 1. So when V has dimension 1 and W has dimension 2n, Rademacher theorem was known, and this was actually, I mean, quite clear to the experts because intrinsic Lipschitz graphs of codimension 1 are boundaries of sets with finite intrinsic perimeter. And for sets with finite intrinsic perimeter, there is a rectifiability theorem that you can exploit and in order to get Rademacher only in this case of codimension 1. So what I did is proving Rademacher theorem in the general case. So now we know that in Heisenberg, every intrinsic Lipschitz map is always intrinsically differentiable almost everywhere. Somehow my proof uses at some point the case of codimension 1 at somehow strange point, but I use it. This theorem has a few consequences which I believe are interesting. Well, first, you can state a losing type theorem for intrinsic Lipschitz graph. So an intrinsic Lipschitz graph can be always covered by a C1 graph, C1H graph, meaning some graph with some intrinsic C1 regularity, apart from an arbitrarily small set. Probably the most interesting consequence for us is the fact that, I mean, in the theory of rectifiable sets, it doesn't matter where you start from intrinsic C1 objects or from intrinsic Lipschitz objects. They are the same, essentially due to if you want, due to this, to the losing type theorem. Okay. And eventually you can recover an area formula for this intrinsic Lipschitz graph. I mean, whenever you have a formula for intrinsic C1 graphs and you have something, a losing type theorem, you can recover some area formula for intrinsic Lipschitz graphs. So my plan would be to give you some ideas of the proof of the theorem. And for that, I will need essentially, basically, two tools. So the first one are some extension theorems and approximation theorems, which I proved. So the first is an extension theorem, as I said. Every intrinsic Lipschitz map can be extended, which is defined only on a subdomain A, can be extended to some intrinsic Lipschitz phi tilde, which is defined an intrinsic Lipschitz on the whole of W. Actually, I mean, what I told you is wrong. I'm able only to prove this result when V is isometrically isomorphic to some Rm. So it's an abelian horizontal subgroup, okay? Which is the case in Heisenberg, okay? But not in, I mean, in general groups, there might be different splittings. This was known for previously just for, in the case of codimension 1. Also, I proved an approximation theorem, again, under the more restrictive assumption that the target V is...
Can you keep the Lipschitz constant, or does it get worse?
It might get worse, but that depends only on the distance D you choose on the group, okay?
So it might get worse means it's wrong that you can keep the same Lipschitz constant. It's
wrong, but also it's not clear how you could define a Lipschitz constant for such graphs. You can keep track of them. Actually, Naor and Young... Can't
you simply define it as the worst opening angle? Okay, you don't have a concept of opening angle for your cone, that's what you mean?
Yes and no. It depends if you look at the sine or the tangent of the angle somehow. Actually, Naor and Young, only for the case of Heisenberg group, and maybe only in codimension 1, I don't remember, they have a sharp extension theorem with the same constant. Okay, but they have to carefully define the Lipschitz constant. I mean, not all homogeneous distances will work, and you have to take some care. But certainly, yes, there is a control on the Lipschitz constant of the extension. So, I mean, you might be forced to pick a larger cone, but you can control how much larger it is.
Just to understand if understood. So you're saying that Maurer and Young are able to prove the equivalent of, I don't remember the name of the
Higgs-Brown.
Higgs-Brown exactly in this setting?
Yes, only in Heisenberg. And I believe only in codimension 1. In any case.
The one which in Euclidean space is completely trivial.
Yes.
The one that you just do with the formula in one line.
Yes. I mean, the second result I'm going to use is an approximation theorem.
No, wait, just one thing. You can do it with one line if the domain is R. Otherwise, you can't do it in one line.
Yeah, but that's what he's saying, right?
Yes.
That they can do it only when it's R. I mean, even for Heisenberg, it's complicated even when.
The codomain.
Codomain.
Okay,
Yeah.
I see.
Okay, the second result is an approximation theorem stating the following. Every intrinsic Lipschitz map phi, that now you can imagine is defined on the whole domain W, can be approximated by functions phi j, which are sinfinity smooths, which are intrinsic Lipschitz with some bounded constant, and which converge uniformly to phi. Okay, so you can always approximate an intrinsic Lipschitz map, provided again you have this assumption that your target is isometrically isomorphic to some Euclidean space. So in particular, it will be horizontal and abelian. Maybe I will skip this. Both results are based on an equivalent definition that I found, which of intrinsic Lipschitz continuity, which doesn't use these cones, but rather allows you to write these intrinsic Lipschitz graphs as level sets of Lipschitz functions. Of course, in general, this has not so much meaning, because any closed set can be written as the zero level set of the distance from itself, right? So what's stated here is clearly false. It's not true that a subset of Rn is a Lipschitz graph along, say, the last direction En, if and only if it can be written as the level set of a Lipschitz function. It's even false if you ask that your function is, so you would be tempted to put into play some assumption on the gradient on the derivatives not to be zero, but that's true almost everywhere by the iconal equation for the distance, for any distance from a closed set. What the correct thing to put is some coercivity in the last direction. So this is an homework for you. I prove that an object S is a Lipschitz graph along the last direction En, if and only if it's contained in the level set of a Lipschitz function whose derivative in the last direction is coercive. So it's bounded away from zero.
Everywhere, not only in it.
Almost
everywhere, but like on the whole space.
On the whole space, yeah, on the whole space. And now, I mean, you can probably imagine that this second definition can be can have some translation in Heisenberg or in Carnot groups. You will require that there is some horizontal derivative, some derivative in the first layer of the algebra, which is bounded away from zero almost everywhere in the space. That works. Okay, the second tool I will need is the notion of currents in Heisenberg groups. In the 90s, Michel Riemann found this object, a complex of differential forms in Heisenberg groups, actually also in contact manifolds. So in a first approximation, let me say that these spaces, D, K, H, are subsets, are subspaces of K forms, of classical K forms. That's not completely true, but in a first approximation, we can think to these spaces as subset of smooth form K forms with compact support. To be more precise, Riemann finds a certain space of k-dimensional covectors, so that these forms are exactly the smooth, compactly supported sections of this space. Okay, so which I will call just Riemann's covector. Okay, and so Riemann finds these spaces D0h, D1h, which we'll call Heisenberg forms, Dn, D2n plus 1h, and in the arrows in this complex are always the standard exterior differentiation D, except at this the intermediate level. When we pass from n to n plus 1, he finds this bloody operator D, capital D, which is a strange second order operator, which picks one n form here, computes second order derivatives and give you an n plus 1 form here. I don't want to say anything more than this. Apart from saying that, again, there are many evidences that this is the correct complex of differential forms from the intrinsic viewpoint. There are many evidences. For instance, there are recent papers of Kleiner, Müller, and Xi, which show that this complex is natural in the theory. And as usual, I guess that at least some of you in this audience know what are currents. A k-current is an element of the dual of the space of Heisenberg k-forms with compact support. For those who don't know what a current is, so maybe the idea is, one should keep in mind, is that currents are generalized submanifolds. In some sense, currents generalize submanifolds in the same sense as distributions generalize smooth functions, for instance. The typical case of a k-current is a k-dimensional smooth submanifold S that you can see as a current which, to every k-form omega, associates the integral of omega on S. So in this sense, this defines a linear operator on the space of k-form. It's a k-current. And currents come with a notion of boundary, which is tailored on Stokes' theorem. So given a k-current T, its boundary, dt, is a k-1 current, which is defined in this way. So the boundary of T applied to a k-1 form omega is the same you get by applying T to the differential of omega. Except that now, in Heisenberg, the differential we have to consider is the one which Riemann tells you. So either capital D or standard exterior differentiation, D, I mean, depending on K. So when K is N, you have to consider capital D, otherwise it's always D. Okay? So this is the boundary of a current.
So Riemann has a Stokes-type theorem for classical, or what, like intrinsic submanifolds?
No.
No?
Because at that time, I mean, so you would need a notion of intrinsic C1 submanifold with boundary, which is also intrinsic C1 somehow, in order to integrate. This is something that I'm doing with my PhD student.
So Stokes' theorem in principle does not exist yet.
Does not exist yet.
So you take it as a definition bona fide that it should work.
Yes, but it works.
Okay, it works. Okay.
Again, it's not trivial, but it works. Okay, so now I believe I can try to give you some ideas from the proof. How much time do I have, by the way?
Well, till 3:30.
So I can speak for an extra 25 minutes?
Yes.
Are you sure?
Yeah.
Okay, so proof of Rademacher's theorem. We have an intrinsic Lipschitz map phi. By the extension theorem, we can assume that it's defined on the whole domain W. Okay. By the approximation theorem, we can find a sequence phi j of smooth maps which converge uniformly to phi and which are also uniformly intrinsic Lipschitz. Okay, then you can probably imagine one can prove that the associated currents, those that to every k form associate the integral on the graph of phi j. Remember, these objects now are smooth submanifolds, so this is perfectly well defined. Now, what happens is that these currents converge weakly star to some current, which I call T phi, and which is supported on the graph of phi. That's super easy. So in this, so what's written here is that there is some current T phi, which is supported on the graph of phi. Okay, so I just define some current on the graph of phi, and I observe that now these guys are entire graphs, they have no boundary. So this current is the limit, weak star limit of a sequence of boundaryless currents. So it's T phi itself must be boundaryless. The boundary of T phi is 0. Now, strange as it can be, this is the relevant, this is the analytic information carrying the relevant geometric information. So this will be precious for us. That I define on the graph of phi some current without boundary, which is supported on the graph. Actually, this current has a nicer structure. It can be recovered by integration. By integration on the graph of phi of what? Integration with respect to this measure. So this is the spherical Hausdorff measure on the graph of phi. You can, in a first approximation, think to this as the standard Hausdorff measure of dimension k plus 1. What happens is that this number k plus 1 is the Hausdorff dimension of this object. So in principle, the graph of phi is k dimension. Is an object of topological dimension k, but it turns out that its Hausdorff dimension is 1. Somehow it contains some vertical direction, which by homogeneity counts twice. Okay. Whenever there is some vertical component in your object, you have to add one extra dimension. Okay, so take it for granted if you want. This is the dimension of this object, the intrinsic dimension of this object. So what are we integrating? The action of t on omega, of tau on omega. So there exists some function tau on the graph which takes values where? In the dual of Riemann's covector. So this guy should, so this tau should be thought of as taking values in some space of multivectors, k of dimension k, of k multivectors. And here we have a pairing between a multivector and a covector, okay, and which we integrate on the graph with respect to this measure. Now, it's tempting to think that this guy, tau, encodes some information on the tangent. It's a multivector encoding some information on the tangent plane, some tangent information on the graph of phi. So if you believe in this principle, you might be led to guess that phi should be differentiable at those points which are Lebesgue points for this function tau, which is clearly measurable. Okay, so this is our guess. When we are at a point where tau is roughly constant, okay, then our graph is roughly flat. And actually, it's close to some plane which will be close to this, or somehow associated with this almost constant tau. Okay, So our claim is that phi is differentiable at all point, actually at almost every point W, so that the corresponding point W, phi W on the graph is a Lebesgue point for this function tau, okay? The tau appearing here, which is given when you follow this, this approximation procedure, okay? So now we do the following. We fix such a point W, and we consider the blow up of the graph at the corresponding point on the graph, okay? So we move the point on the graph to the origin and we dilate. In principle, we might have several blow-ups, several possible blow-ups, okay? Our goal is proving that all blow-ups are the same and actually that they are a vertical plane, okay? That's our goal. Okay, fix one among the possible blow-ups, call it sigma. So you can recover sigma by blow-up, meaning that there is a sequence of scales along which, when you dilate according to these factors, your graph is converging to this sigma, okay? And now you could do the following. So consider, sigma is a limit of blow-ups at some scales of the graph of phi. Now look at how the current that we define on the graph of phi behaves under this dilation. So technically we are considering the blow-up of T phi along this sequence of scales. This is the current on the graph of phi. By blow up of a current, I mean the Wickster limit of the push forward of T phi under these translations and dilations, something quite natural. What happens? Now, your graph is approaching sigma, is converging to sigma. You can prove that the current T phi on the graph under dilation is approaching some current T sigma defined on sigma, which is again a current that you can recover by integration on sigma. And now the integration is against a constant multi-vector tau bar, which is exactly the value of tau at the Lebesgue point, W phi W bar, okay, which is an element in this strange space of multi-vectors. Okay, I mean, when you dilate, right? When you dilate the graph of phi, you know that, I mean, at smaller and smaller scales, tau gets closer and closer to a constant, which is tau bar. So you can imagine that under blow up, you are converging to some current T sigma, which is associated with integration on the blow up sigma against this fixed vector tau bar. And again, T sigma is a limit of boundaryless currents, so it is itself boundaryless. Okay, so let me summarize what we have done so far. This is the graph of phi, again, in this direction, okay? And here is depicted as a one-dimensional object. We approximated the graph of phi, which in principle is very bad, by smooth objects, which are by smooth graphs which are converging to the graph of phi. And this allowed us to define a current without boundary, T phi, on the graph of phi. Now we fix the point, which is a Lebesgue point of the function tau, and we perform a blow up at that point. We obtain some object sigma on which some current T sigma is defined, which is obtained by integration on sigma of a constant multivector. Now what happens here is that here is the point where I use the codimension 1 result. You can prove this strange property that at almost every point on the graph, in principle, you might have a lot of possible blow-ups, but at almost every point, all of the possible blow-ups are vertical. So they are invariant in the vertical direction t. As in this picture. And in fact, in this picture, there is something which is right now it's a surface, while before.
So here you are in the Heisenberg group. The vertical direction is the last coordinate in the Heisenberg group.
Exactly. Exactly. If you accept this magic, now we are almost done. Why? Because it's fairly easy to prove that whenever you have an intrinsic Lipschitz object, and sigma being the limit of dilation of intrinsic Lipschitz graph is itself an intrinsic Lipschitz graph, which is also vertically invariant, then it's Euclidean Lipschitz, as in this picture. Being Euclidean Lipschitz means that at almost every point, your blow-up is a plane. And in this case, where everything is vertically invariant, Euclidean or Heisenberg blow-ups give the same guy. So remember, our goal was to prove that sigma was a plane itself and actually a unique plane, a fixed plane. Now, what we do is a second blow-up. So we fix, so at almost every point P in this first blow-up sigma, we can perform a blow-up of sigma to get a tangent plane TP sigma. And exactly as we did before, together, so in the blow-up argument, when we blow the submanifold up, we can also take track of the current, of the associated current. The blow-up of the current will be some current concentrated on the tangent plane. Now, our goal is to prove that this tangent plane is unique, okay? It doesn't depend on P. And if we prove this, then sigma itself was a plane. And if we prove that this TP sigma is a fixed plane, which is determined uniquely by tau bar, that's what will happen, then actually sigma will be that unique plane determined by tau bar, which means that there is just one possible blow-up sigma, one plane determined by tau bar. Okay, so as I said, at almost every point of sigma, the blow-up, Euclidean or Heisenberg is irrelevant now, is a plane, a K-plane, and if we call T sigma P the blow-up of the current that we had on sigma, now you can probably believe me, the blow-up, I mean, the second blow-up of the current is a current that you can recover by integration on the tangent plane of that fixed vector, multi-vector tau bar. And again, this guy is limit of currents without boundaries, so it's boundaryless itself. Now we have a current which is obtained by integration on a plane of a constant vector. In Euclidean, I mean, in the classical case, there is a Constancy Theorem that tells you that if you want this current to be boundaryless, then this guy tau bar is forced to be the tangent multivector to this plane. Here is a, so in Heisenberg, I proved a suitable version of this Constancy Theorem, which in the end, for our problem, is telling us that this plane, the tangent plane, is uniquely determined by tau bar itself. So in this picture, this plane, I mean, there is just one choice for this plane, which means that there is just one choice for this sigma, the plane determined by tau bar in a unique way. I'm hiding a lot of dust under the carpet here. There are some funny stories about this. I don't have time to go into these details. Eventually, what we proved is that there is just one possibility for sigma, the unique plane determined by tau bar, tangent to tau bar in some sense. So after I found this result in Heisenberg, I was tempted to prove Rademacher theorem in the widest generality, for instance, in groups of step 2. That would be a natural guess, because, for instance, in step 2, we have Rademacher in codimension 1. So it was quite natural to try to, but actually, quite surprisingly, we came up with a counterexample with Antoine Juliat and S.Nicolussi Golo. We found a 4-dimensional group, which is first Heisenberg times R. Forget the splitting. The splitting is some 2-dimensional subgroup W and another 2-dimensional subgroup V. And we were able to produce an intrinsic Lipschitz function phi, for which Rademacher does not work. And phi is pretty easy. Okay, so it has 2 components. The first one is 0. The second one is a function u of t, where t would be the vertical variable in this h1 factor. And u is chosen to be 1/2 further continuous, and this can be produced. This limit does not exist for any point t. So this limit, so this object here is somehow the Hölder difference quotient, right? Which we know is bounded. You can produce a 1/2 Hölder function for which this limit does not exist at any point. There are classical ways of producing such a function. I guess I also have some picture later. Now, what happens is that this map is intrinsic Lipschitz. And you can probably believe that this is due to the fact that the function u is 1/2 Hölder, right? So u depends on t, which is the direction where we have which weights 2, right? Where the dilation scale by a factor 2. So you can probably believe that this 1/2 Hölder continuity translates into, due to that factor 2, translates into an intrinsic Lipschitz continuity. But it's nowhere differentiable, because being differentiable would mean that in the blow up, you are converging to something vertical. And this would mean somehow that this numerator here is a small o of the denominator. So you would like this ratio here to converge to 0. So having the intrinsic differentiability would imply this guy to converge to 0. And that's not possible. Actually, one can construct phi, so this phi is quite irregular. You can produce such a phi, I mean, by properly defining u, you can produce examples where at every point there are infinitely many blow-ups, none of which is a subgroup, okay? You might be tempted to say, okay, at least maybe we have a lot of blow-ups, but there will always be at least one subgroup. This is something which happens in the theory, I mean, at least in a few similar problems. Actually, no. You can produce an example where you have infinitely many blow-ups at every point. No blow-up is a subgroup. And this tells you that this graph is purely unrectifiable if in your definition of rectifiability you use intrinsic C1 objects as building blocks. Okay, so in this setting, rectifiability with C1 building blocks and with Lipschitz building blocks give you different theories. Actually, the fun thing is that, if I remember correctly, the submanifold, which might look quite wild, is also a minimal submanifold because it has a constant tangent, intrinsic tangent somehow. So also the theory of minimal submanifolds fails, apparently, in this setting. Okay, so I guess I will skip the construction of you. Thanks a lot for your attention. Questions?
Can you still show us a picture of the construction?
Okay.
It's skipped over, but
Sure. This is a nice way to produce Hölder continuous function. You start from the identity, right? And then you select two, you divide your segment 0, 1 into 3 segments. Okay, first one, second one, third one, don't forget about these numbers. And then you put in each step, so this is the first step, this is the second one, third one, fourth one. In each step, you start from your previous picture and you put 3 copies of it, scaled by different scales in length and height. Okay, so here from 049 and up to 8 2/3, we have one copy of what we have here in the square. Here from 5/9 to 1 and from 8 1/3 to 8 1. So in this rectangle, if you want, we have a scale copy of this square. And here in the smaller rectangle, we have again a copy of this square with but upside down in order to preserve continuity. And you repeat the construction, okay? So in this first rectangle, we put a scale copy and distorted copy of what we have here. The same in this rectangle here, and also in the middle one, okay? Again, upside down. And again here. So you go on, and in the limit, what you get is a 1/2 Hölder continuous. I mean, if you choose these parameters, you get a 1/2 Hölder continuous function with the desired property. Of course, you can produce, I mean, if you vary the parameters, you can find any.
like this devil's staircase function, but like with slightly different proportions.
Yes.
That would be this like function that's.
It's a counter type construction.
Do you think you could also construct such a function using something random? So like Brownian motion itself wouldn't work because it's not 1/2 Hölder. But if you play with the covariance function a bit, you might be able to kind of.
Might be.
At a certain point, you stated the extension theorem for Lipschitz functions, going morally from Heisenberg to Carnot groups into Rm. And you said that when n is equal to 1, the extension is sharp. And you stated that you're proving a non-sharp version. You know that the sharp version is false?
I don't know. I don't know that. That I don't know. Actually, I mean, it's very unclear what should be the notion of. There might be some Kirchhoff-Brown theorem where you preserve your constant, but then the point is carefully defining what you mean by Lipschitz constant or aperture of the cone. So there should be geometrical issues in the selection of the cone around the target V.
So your problem is that it's not like the distance is not going to be a product distance. So it's not obvious what you have to do, I guess, right? So that's what might be confusing us.
Yeah, actually.
It's not simply you can say the distance on the target is less or equal than the constant times the distance.
Yeah, something I forgot to say is that this notion of Lipschitz continuity is very different from the standard continuity, Lipschitz continuity from, I mean, this W is a subset of G, so it carries its own distance, same as V. So you might be tempted to consider maps which are Lipschitz in this more classical sense. The two notions agree when the splitting gives you a direct group, a direct product.
But otherwise,
everything is so twisted that they give different. And actually, probably, it's possible I'm not saying something correct, but it might be that there are maps which are Lipschitz from W to V when you put the distance you have in G on both of them, whose graph has fractal dimension. It could be.
So as an aftermath of your proof, the current that you find by approximation as unique, right? Which wasn't obvious.
Yes, it wasn't obvious. It's not only unique, it's the natural current that you can put and that gives you integration on the graph.
But if it's unique, it's kind of the natural current.
It is.
I mean, it's the only one that you can possibly land on if you make a sensible approximation.
Of course.
And this wouldn't be obvious, like you wouldn't know how to prove it by making estimates on say, two sequences which are approximating the same graph. Because your approximation theorem doesn't come with something that you can put your hands on and make computations.
No. It's somehow it's a C0 approximation. You would need a sort of C1 approximation.
Well, not necessarily, no, because you have a C0 approximation, but you could say, well, sure, if I want to estimate, like, very strongly, but you could try simply to fill the space between two of the approximations by putting a clever current of higher dimension whose boundary is the difference of the two, right? I mean, if you're trying to, like, you could try to prove something very weak to show that the thing is unique, which
I haven't proved.
Maybe requires.
But actually, what you say seems feasible. Because in this approach where you use this alternative definition as a level set, you can play with the level set. Actually, it's not just a sequence. There is a whole continuous family converging. You can really use what's in between, as you said. You can really define it in some meaningful sense.
Okay, yeah. Does not seem to be any other questions, so thanks, Davide.